Let's get started by creating a playground. On a Mac, open Xcode. We'll use Xcode 8, which has Swift 3 support built in. Go to the File menu and select New, then Playground. You'll need to name it and pick a platform. For our examples, it doesn't matter which platform you choose, but iOS is the most popular. Finally, save the playground, and then we're ready to go. The playground came with some code already in place. Before you delete it, let's take a look at that last line. var str equals double quote hello playground double quote. In the grayer area to the right, you'll see the contents of the variable called stir, and the playground will update these each time the variable changes. Let's delete just the one line of code that begins with import. The playground automatically reevaluates, and we still see the contents of the string in the sidebar. Playgrounds were specifically designed to make learning Swift easy, without concerns of a larger application in place. We didn't need to import any modules to make this happen. Now, delete everything in the playground and type the following. Type print open parentheses double quote hello playground double quote close parentheses. While you do see the text show up in the sidebar, the print function sends text to the debug area. Click the button in the lower left-hand corner of the playground window to see it. The important distinction is the debug area will show all the text sent to the print global function, while the sidebar will only give a summary of each variable at its point in the code. Sometimes the sidebar will be all you need. When it comes to debugging more complex behavior, you'll want the debug area as well. While we're down here, let's talk about that blue button. It's the Evaluate button. If we hold down the mouse, we can choose to evaluate only manually when the button is clicked, or to let the playground reevaluate for us. Most of our code examples will be simple enough that live reevaluation is fine. Depending on the machine, we may decide to run manually. Type this into the playground. var a boolean colon capital bool equals true. This line of code creates a Boolean variable. We start with the keyword var. Next comes the name of the variable. All variable names in Swift should be lower camel cased. Next comes the type specification. It's a colon followed by the type name. All type names in Swift, both built-in types and user-defined types, should be upper camel cased. Next comes the initial value, which is introduced with an equals followed by the value true. You may have read that Swift has type inference, so we don't need to write the type. That's true in many circumstances, like this one, so let's remove the type. This is fine as far as it goes, but let's consider that I forgot a boolean was supposed to be a bool, not an integer. This is also fine until I try to use the integer as if it were a bool. Let's put the type back in. Notice that the compiler now tells me about the error. This is great. Swift is a much safer language than C or Objective-C, largely due to its type system. If I had a function which returned a more complicated value than just a bool, I might get confused or forget what the exact type is. The compiler goes along with me, checking as I write, so I find including the type names in places where they can be inferred actually helps me. It also helps me read the code later on. Type inference slows down Swift compared to compiling C or Objective-C, and including explicit types can speed it up. So for both these reasons, catching mistakes up front and faster compiles, I always include explicit type names. So how would I store an integer? Type this, var an integer colon int equals 14. Capital INT is the type name for a signed, machine-sized integer. What if I wanted an unsigned integer? That's capital U int. Suddenly, there's this red stop sign in the gutter. Click it and it tells you about the compile time error. We can't just create an unsigned integer with an int. We'll need to convert it explicitly. Change the unsigned line to this. Capital UNT, open parentheses, then an integer, then close the parentheses. Now the compiler is happy. We've used what's called a converting initializer to make a uint from an int. We'll talk more about init methods another week. There's still a problem here. Change the literal value to say -14. Now we get a red stop sign and the text is foreboding. Execution was interrupted. This is no compile time error. This is a runtime error. Unlike compile errors which prevent me from distributing code that will crash, runtime errors are crashes. We want to avoid these, all of them. We'll cover how as we progress through the lessons. For the moment, just notice that as you read Swift APIs, you'll see a lot of int where you might have expected uint in another language. There are two reasons for this, not just to avoid unnecessary crashes, but also to reduce the impedance mismatch of converting from int to uint and possibly back again. So how would I create an integer of a fixed number of bits? As an example, a 1-byte integer. Well, that's capital U int 8. Swift provides fixed with signed and unsigned integer types with 1, 2, 4, and 8-byte counts. They're named by the number of bits, so for 2 bytes and signed it would be int 16. Today we've learned that playgrounds help us learn the Swift language without requiring a larger application in place. We began learning about built-in types like booleans and integers. We also learned the difference between a compile time error and a runtime error. Type safety, even between signed and unsigned integers, now that's Swift.